So now, today we will finish the topic on Boolean algebra, okay? And then next meeting we'll proceed with a new topic called computer hardware, okay? So we may not we may not consume the whole 1 hour and a half today, okay? Because I'm also going to attend a meeting at 11 o'clock. So yeah, I need to prepare a little. So any questions so far? So last meeting we have solved. There's a correction, by the way, in item 15, which I haven't corrected yet, but the answer in the solution is correct. Okay. Yanto and Ramirez. So the answer in the solution is correct. Okay. You can just go on answering it. I haven't checked it yet because I had a problem with Degler earlier. No? Langreo is here. So today we are going to discuss the most common basic logic circuits. No? We are also going to show them in we're going to show them in Sidor logic, how they really work. Okay. Now, if you log into our Degler class, the next topic is basic logic circuits. It's also actually included in the first slide, but I have created a separate slide. Ligtas na balik eskwela. So there's a news. Ligtas na balik eskwela. How can we go back there? Even if you're vaccinated, you can carry the virus. Okay. I think it's too early for college students to be there. Maybe for preschool students. Yeah. I don't know, but I'm open to having face-to-face classes once a week. No, I think that's better. No? And then the other class will be online, no? On and off, no? Because it will also help ease out the traffic and lessen down the students. Excuse me a while. Text na po. Okay. Sorry for the disturbance. Okay. So there's a part here which states basic logic circuits. That one. Can you download that yourself? Yes, Ramirez, I've already checked your okay. Basic logic circuits. You can download this. No? Anyway, let's open the slide. I've already downloaded it. No, myself. Where is that? Oh. Let me just download it again. Let me cut it here. Okay. It's already there. Sorry for my it's here, no? The basic logic circuits. Okay. What are the common applications of logic gates? I'll check the attendance later again, no? What are the common applications of first of all, Moria and what's that? Ramirez, I think I've checked already. Yeah. Anyone else? Miss. For a while. A while. Okay. So the applications of basic logic circuits. Now there are many applications, no, especially calculators, computers, no, cell phones, and so many others. No? Now these logic circuits make use of the basic gates. Okay, we will try to build them in Cedar Logic. I've already created them. I'll create one of them for you now, and then we'll open a set of circuits which I have created before. It's a very time consuming. Now, one function is called a binary decoder. Okay, this is used usually on an output side of a device because the internal system computes in binary. Most internal systems compute in binary, and the display is in decimal. Like if you have a calculator, the calculator deep inside computes in binary, but before it displays the result, it converts it into decimal. So that's why it's called a binary decoder. It decodes. No, it's called a decoder because the input side is binary. Okay, remember that. No, if the circuit has an input in the binary form and outputs it to another form, that circuit is called a decoder. It decodes because our code is in binary. Okay, for example, it makes use of this. No, for example, if you want to, you can use an AND gate. For example, if you want to decode the value 1011, okay, you can use an AND gate with the third bit with being inverted. So this is 1011. Okay, a zero means a gate, or rather an inverter, and a one means just a plain connection. Okay, do you follow? So we have here a 3-bit binary decoder. It converts 3-bit input into decimal, like here. No, this is our table. No, if the value of the input is 000, D0 is 1. Okay, we will output this to a decimal display which outputs 1. D0 is 1. If the value is 001, all of the rest, this D1 to D6, which is the output, will be 0 except D1. Okay, except D1. Okay, and then if the input is 010, all of the inputs will be low except D2 because 10 is D2. If the input is 011, all of the inputs will be 0 except D3 because D3 is 011. We follow and so on and so forth. Okay, so the circuit looks like this. No, okay, let me build this in in Cedar Logic. You can build this even without a copy of the circuit because we know that the first is 00, the second is 110, the next is rather the next is 001, the next is 010, the next is 011. Okay, do you follow? Okay, so let's try to build a binary decoder using Cedar Logic. The rest of the circuits there, I've already created them. And by the way, you can download it from our Dagler site. No? Basic Cedar Logic circuits in Cedar Logic. Okay, you can open them and try it. Okay, try it yourself. This is a very interesting set of circuits. Okay. So let's open our CDR logic. Any questions so far? No. Let's see. So the first week is we are going to encode. Our input will be in 3 bits. Okay, so if our input is in 3 bits, the number of values we can store is 8 from 0 to 7. So let's make a decoration. This will be our input. This will be A0. This will be A1. This will be. We'll try to spread them further apart because we'll have a lot of output. Okay, A2. Okay, and then we will have in outputs. Dito natin let's put here first. It's here. This will be a 3-bit decoder. Okay. So this will be our output, D0. I'm just doing this to show you how it's done, okay? But the next time around, I'll come up with a prepared circuit. It's very time consuming to do this. D1 to D2 to D7 is our set of outputs. Okay. Can we align this? Is there a way to align this? You right click not to change the orientation. Okay, because later I'll show you gates with different orientation. The problem with this is we don't have a tool for alignment, no? Unlike in other platforms. No? B5. So you have to align this manually. That's a bad news. No? Can you download circuit binary decoder from the net? It's a CDR logic circuit. We follow, and then we will need a lot of connectors here because you will need 8 connections. No, from one input you may need at most 8 connections from D0 to D7. Okay, do you follow? So how do we make 8 connections from one point to another? Okay, we can make we can interconnect connectors to other connectors. Do you follow? So if you connect 4 connectors together, you will have a total of 9 connections. Okay, 9 connections because you will spare one of the 4 connections in a set. Do you follow? No. So we will need 4 connections. Unfortunately, we need 4 connections for each. No. Okay. Like this. Do you follow? We cannot copy and paste also. Therefore, no. You have to. Okay. So now we have a total of 9 connections. No. This is okay because again. Let's move this first. Okay. We have a total of 9 connections each. You get my point? So this is only the tedious part, making the 9 connections. But aside from that, no, everything is easy. The rest is easy now after we've done this. Okay, you follow? So we'll do this again. Unfortunately, we just have to do this because there are too many connections to be added. Wala tayong magawa dito, no? Just like that. We'll have to spread this a little farther apart. So that it will be easier kasi mahirap din mag-connect eh. Okay. Mahirap din mag-connect if they are too close to each other. Okay. Ganon din. Okay. We connect this to that. Okay. So the first value is 0, 0, 0. 3 zeros. So we'll put it in an AND gate. So we need a 3 input AND gate. Like that. And then we need 3 inverters because this is 0, 0, 0. Ito na lang, no? So the number of zeros determine the number of inverters. Okay. You follow me? I hope you're following me, no? Okay. We'll connect it to this and we'll connect it to that. And then we'll connect it to D0. Can we move it up? Okay. And then we'll connect this to each of the input. First to A0. Second to A1. Then third to A2. Do you follow? So now we can test if it's if the value, all the rest are zeros. Take note that D0 is red, which means that the value in the input is 0. It's 0, 0, 0, right? If you make one of them to be 1, it becomes a block. Okay, so there's now the decoding of 0 into decimal. Okay, now we'll decode 0, 0, 1. So we'll need only 2 inputs, no? 2 inverters here for the 2 zeros because we will have 0, 0, 1, right? Dalawa lang, 0, 0, 1. Sorry. Then we put it here. No. Align it. No. Kasi nag-connect siya eh. You follow? And then the first one we will connect to A0. So we have that, no? Oh, hindi siya nag-connect. Nag-connect siya. So did it connect? We'll delete this. Nag-connect siya sa A1. I'm sorry. No? Dapat ito yung sa A1. Kaya nga ganun. Okay? So we'll connect this to A0. That's okay now. And then we'll connect this to A1. Then we'll connect this to A2. You follow? So for example, if you will have 2. Okay, so 2 is 0, 0. Now we'll have 1. No? We'll have 1 here. So that's why here we have a D1. 0, 0, 1 is now converted to decimal 1. Okay. So we'll need a third gate. Huh? So now we need 0, 1, 0. So we also need two invert gates. 0, 1, 0. So we need it on the first and the third. The third and the first. Okay. Okay. And then we'll connect this to A0. Move this. Sorry. So naman eh. we lost one. Saan yung nawala? This one. We have to connect here. I-move na lang natin ganyan. Okay. So this one is connected to A0. This one is connected to A1. Okay. Move natin pataas para hindi magano. Wala, dito lang talaga, no? And this one is connected to A2. Okay. Do you follow? That's 2. And then we need 3. 3 is, what is 3? 0, 1, 1, right? 0, 1, 1. So we need two NOT gates also. No, 1 NOT gate, 0, 1, 1. Okay. So we need a 0 here. D3. Okay, and then we'll connect this to A0. Okay, this we connect to A1. Wala na tayong iba, no? So we'll just have to connect it here. Bakit siya nagkaganon? Yeah, this is A1. Because this is A1. This is A1. Is it all right? Okay. Kasi A1 ito eh. Then A1 din ito. It's all right, no? And then we'll connect this to A2. Okay. Let's try to make, when can we have a D3? We have 0, 1, 1. Yes, we now have a D3. It's 0, 1. This is a 2. Okay. This is a 1. Okay. This is a 0. So take note, no? We are now converting. Simon is here. We'll check the attendance again. D4. So we need another AND gate. D4 is 1, 0, 0. So therefore we need two inverters. 1, 0, 0. So we need to connect this to A0. That's okay. We need to connect this to A1. That's also okay. And we need to connect this to A2. That's also okay. And then we connect this to the output B4. Ano lang para we have space. Let's try 4, 1, 0, 0. Okay. That's the 4. Okay. This is 2. This 1. This is 3. Okay. Therefore, take note, no? It converts from binary to decimal. Okay. Simply by using an AND gate, no? Because an AND gate for D5. What is D5? 1, 0, 1. So therefore, we need only one inverter. So we only have 1, 0. Okay. We'll connect this to A1. A0, sorry. A0. And then we connect this to A1. Okay. And then we connect this to A2. Okay. Let's try we'll connect this to D5. Let's try 5. Yes. No, that's 4, no? 5 is 1, 0, 1. Yes, that's 5, no? Wala pa tayong 6. We don't have a 6 yet. No? So wala pa. So for 6, we will have 1, 1, 0. So we need another AND gate. And then we'll need only one inverter because we have 1, 1, 0. Okay, so we'll connect this to A0. Okay. Then we connect this to A1. No? Okay, and then we'll connect this to A2. And then we connect this to D6. Let's find out if we will have 6. 6 is 110. 110. That's 6, no? Do you follow? Do you follow? 110. Now we need a 7. A 7 is 111. So we don't need any AND gate. Do you follow? We need to connect this to A0. Wala na siguro masyadong problema dito, no? And then we'll connect this to A1. And then we'll connect this to A2. Okay, let's try a 7. A 7 is 1 or 6, no? 1106. 111 is 7. Okay, do you follow? Do you see the, no? So if say 101, 101, that's a D5. Okay, 100, that's a D4. 4, no? And then we'll have, let's go back. 000, that's D0. 001, that's D1. 010, that's D2. 011, that's D3. Okay, and then we'll have a 100, that's 4. 101, that's 5. 110, that's 6. 111, that's 7. So you see the conversion. It's a 3-bit decoder from binary to decimal. Now, let me save this now. Okay. Worksheets and circuits. This is 328 decoder. Yes. Okay. So that's a 3 to 8. Okay. Now let me open a set of circuits which I have created before. No, these are all the basic logic circuits. So this is the decoder in page 1, and we have an encoder in page 2, and we have a half adder in page 3. We have a full adder in page 4, and we have an ALU in page 6. You follow? There are others which I did not discuss anymore because they're very self-explanatory. No, you follow? So this is the decoder which I've just shown you. No, so if you say 000, that's 0. 001, that's D1. 010, that's D2. 011, that's D3. Then we'll 100, D4. Now, may naputol ito. This should be here on. I'll have to upload it. 111, that's 110, that's D6. I'll have to upload. I'm sorry, no, before I forget. So, putol, no? Before I forget, I have to upload this because the other students are also going to use this. So it's always good to update this right away. It's here, no? Ito. We're on the wrong thing. Let tayo, no? Scroll up. Ito, no? Should be it. Bakit mali ang pinupunta natin, no? Sorry, no? Bakit tayo napunta sa maling, ano? Where are we now? You're always, maybe I have created the wrong link. It's a good thing that I have to change it now, no? So this is the wrong thing. No? So mali talaga yung na-upload ko doon. We delete this. And then we'll upload this. No, hindi. Kailangan natin, this should be a zip file. Okay. Sometimes, no? This is a slides dapat sa worksheets. Basic logic circuits. Ito pala na. So we'll drag it here. Okay. So it's there. I've updated it already. No? It's because I made a mistake in this decoder. If you have 111, it's D7. Okay. That's the decoder. Any questions so far? Be sure. No, I'll meet you later. Okay. That's the decoder. The second is an encoder. No. What is an encoder? How are they different? If the input, if the binary is a system number is on the input side, it's an encoder. If the binary system is on the output side, okay, it's an encoder, which means it's going to encode it to binary. Like in this example, we will have a decimal to binary. Now, when is this used? On the input side, no? And a decoder is used on the output of a system, of a digital system, no, to a display. And then an encoder is used on the input side. Like for example, on a keyboard, if you look at the keyboard of a calculator, it's in decimal, you know. So every time you press a key from a keyboard, no, it will be converted into binary before it's processed by the system. So there should be an encoder between the keyboard and the digital system. Okay, it's like this, no? So this is your keyboard. If you press 0, it will be 0, 0, 0. If you press 1, it will be 0, 0, 0, 1. Now, like unlike the decoder, the encoder uses an OR gate. Do you follow? Do you follow? No? Do you follow? So let me do that in Cedar Logic. That's in page 2. This is the encoder. When you press 0, this is like a keyboard here. When you tap 0, the value is 0. When you tap, for example, when you tap 1, the value is what? 0, 0, 0, 1. Do you follow? And when you tap, for example, 2, it will 0, 0, 0, 1, 0. If you tap 3, for example, no, if you tap 3, it will become 0, 0, 1, 1. Take note, it converts, no, from decimal to binary. When you tap 4, it becomes 1, 0, 0. This is a keyboard here. When you tap 5, it becomes 1, 0, 1. Okay. When you tap 6, it becomes 1, 1, 0. Okay. When you tap 7, it becomes 1, 1, 1. When you tap 8, it becomes 1, 0, 0, 0. And when you tap 9, you can only tap 1. It be one keyboard at a time, 1, 0, 0, 1. Do you follow? So this converts from decimal to binary. So this is usually used on the input side. So take note of the difference between an encoder and a decoder. No, if the binary system is on the input side, it's a decoder. If the binary system is on the output side, this is the output. No, it's an encoder. Okay, do you follow? Any questions so far? Half adder. Okay, what is a half adder? A half adder is a 2-bit adder which computes the sum and carry. No, the sum is done using an XOR gate. Is that correct? XOR gate? Yes, because 0 plus 1 is 1. 1 plus 0 is 0. But 1 plus 1 is 0. So kung OR ito, if you're using an OR gate, 1 plus 1 is 1, which is not correct. So we're using an OR gate. Now a carry is using an AND gate because there's only a carry if both are ones. For example, 1 plus 0 is 1, carry is 0. Okay, 0 plus 1 plus 1. 1 plus 1 is 0, carry 1. Do you follow? No? Okay. 0 plus 1, it's 0. As it's 1, carry 0. Do you follow? Let's do 1 plus 0 again. 1 plus 0 is 1, carry 0. That's a half adder. Any questions so far? A half adder adds 2 bits. Okay. Any questions? Now a full adder. Now in a full adder, addition is done using 2 XOR gates. No, the first XORs X and Y. The second XORs the XOR of X and Y with the previous carry. What's the formula here? Here's the formula for enable switch. We'll also discuss that. No, the full adder. Okay. Okay, so it's an XOR, but by the way, the sum is an XOR of the carry and the XOR of A and B. Do you follow? A, B, and C. We are adding three here. No, it's called a carry because there's a carry from the previous addition. Okay, it adds 3 bits. This is an XOR, no, of the carry and okay, the XOR of X and Y. Do you follow? Okay, let's do that. No, 0 plus 1 is 1, carry 0. Diba? 1 plus 0, it's 0. No, 1 plus 0, it's 1, carry 0. 1 plus 1, it's 0, carry 1. Okay. 1 plus 1 plus 1, it's 1, carry 1. Do you follow? A full adder does a 3-bit addition. Any questions so far? Okay. Now we'll come to a more important circuit. It's called an ALU or an adder subtractor. It's a 4-bit adder subtractors because this actually adds A and B. Do you follow? And it can also does a subtraction if the subtract here is high. Now we have a special circuit here called FAs. We have 4 FAs. Now inside this is a white box representation, which means there's a circuit inside. What's the circuit inside? The circuit inside is a full adder like this. Do you follow? So each of this has X and Y and C. X and Y and C. And it will also have an output of sum and carry. Now the current carry is sent on to the next adder as the next carry, because that's how you do addition. Diba? To do addition of A and B, you add A0 and B0. And the carry you use to be added to the addition of A1, B1, and C1. Do you get my point? And the carry of A1 and B1 is added to A2 and B2. And the carry of A2 and B2 is added to A3 and B3. And the last carry is an indicator whether the output is positive or negative. If the last carry is 1, the output is positive. If the last carry is 0, the last output is negative. So this is an adder subtractor. For example, we'll add 5, 1, and 2. No? So A, for 5, we will have 1, 0, 1. No? That's 5, no? Okay, so you already know 5 ba yan? 1, 2, 4. Yes. Because 0 is okay? Do you follow? Okay. 1, 2, 4. Now, there's something wrong with our no. Now this is not A3, but it should be A2. 1, 0, 1. Okay. And B is 2. For B is 2, we'll have 0, 0, 1. Okay. Do you follow? Okay. So we have A as 5 and B as 2. And the sum is 1, 1, 1, which is 7. Do you follow? Do you get my point? Now, what happens if we will do a subtract? If we will do a subtract, B is converted into 2's complement. Take note that when S is subtract, no, all B's are XORed to S to a 1. XOR to a 1. What will an XOR do? An XOR will convert into 1's complement. Okay? Do you follow? It's in the notes, no? So for example, 0 XOR 1 is 1. Okay? 1 XOR 0, 1 XOR 0, no, 1 XOR 1 is 0. No? 0 XOR 1 is 1. 1 XOR 1 is 0. Do you follow? So the XOR gate will convert into 1's complement. Any questions? Now, you may ask, how is the 2's complement converted? How is B converted into 2's complement? Okay? Diba, in 2's complement, we are going to add 1 to the 1's complement. Take note that the 1 here, if subtract is 1, it's also added as 1 to the first carry of A0 and B0, effectively adding the needed 1 for the 2's complement. Do you get my point? So let's do that, no? So we will have 5 minus 2. So we'll do a subtract, okay? 5 minus 2 is 3, right? So 3 is 1, 1, 0, 1, 1. Do you follow? And C4 is positive, is plus, which means that, okay, the answer is positive. Okay? Do you follow? If we do this, if you do the unsubtract, that's 5 plus 2 is a 7. Okay? 5 plus 2 is a 7. Why did we have a 2's complement? No. The 2's complement, by the way, will have to be determined by a subtract. This is an addition, so this is not in 2's complement. Do you follow? Okay? We should have ANDed this C4, no? Sandali lang, no? I-AND ko itong C4 with a subtract. Okay? We need an AND gate here. Dito dapat. Okay. They follow. And then the C4. Okay. So this is in 2's complement. Let me just upload this again. Okay. Let me upload this again, no? So may correction pa. Okay. Do you follow? We have 5 plus 2. Bakit ganun, no? This should be 5 plus 2. Kasi this is a 0. So we should have a not. We should have a not kasi this is a positive number. Okay? Let's put a not. We'll remove this. What we'll need is a not and not gate. 2 input NAND gate. Okay, and then we put it here. Okay. So positive ito. Do you follow? If we do a subtract, okay, let's do a subtract. Mali, no? Because this is a 5 minus 2. 5 minus 2, it should be a positive. Positive 3. Bakit hindi, no? Baka hindi, nagkamali lang ako ng ano kanina, no? Let me do that again using this. Okay, nagkamali lang ako ng ano kanina. Yeah, that's correct now. AND gate, no? So this is positive, no? Okay. 5 plus 2 is 7. No, 5 minus 2 is positive 3. Right? We'll do a sub plus. What happened to the plus? Tanggalin ko lang muna ito, no? Let me remove this. Okay. Dapat, no? This should be a because this is a positive, ano? Okay. I-OR natin ito. So mali yung aking ano, no? We need an OR gate here. Okay, and then we need a NOT gate. Because if it's a subtract, mali yung pagka-connect, no? What's this? This is a okay. So this is a 5 plus 2, so it's positive. Let's do a 5 minus 2. Okay, so tama na ito, no? This is a 5 minus 2. This is a 3, positive 3, right? And then if you subtract 5 plus 2, that's positive 7. Okay, this should be a red. Okay, what will happen if we will have 2 minus 5? 2 plus 5, no? So A is 2, so we'll have this one, and B is 5, so we'll have this, this, and this. B is 5, no? So 5 plus 2, that's 7, positive 7. Okay, what will happen if we subtract? Okay, 5 minus 2, that's negative 3. Do you follow? If we'll add, that's 7. That's positive 7. If you'll do a subtract, this is negative, right? Take note, this is negative, no? No? Do you follow? So this is an arithmetic logic unit, which already does subtraction and addition at the same time. Do you follow? We need this circuit so that we will know if the last, because the problem with the previous one, if you're going to do an addition, it's going to have a black here, which means it's negative, so it should not be, no? Do you follow? Do you follow? Any questions so far? So I'll save this and yeah, update it one more time. Okay, do you follow? You can test the circuit. So what's the next thing? 6. Wala na, no? Okay, now let us look at the other, no? The other circuits, no? Half adder, full adder, enable switch. An enable switch. What an enable switch does is it converts, no? It's like an if then else. If enable is high, the output receives the input. If enable is low, the output is just 0. It doesn't receive the input. It's like a switch. It's like a faucet, no? That when you turn on the faucet, you will get water. But if you turn off, you get nothing. Do you follow? Maybe we can construct this, no? Enable switch here. We'll have A3. A2. A1. And A0. Okay. And then we'll have AND gates. Excuse me, I just right click, no, in order to connect, to make connections, no? So we need an input. Okay. And then we need a connector. Then we need another input. Then we need a decoration. And then we need outputs. We decorate this also. Y equals A if enable is high. So it's like an if then else in a programming language. Okay, we connect it here. Okay, do you follow? Okay, so you'll say enable. Okay, so y is equal to c, y is equal to a. Shall we say a is 1, 0, 1? Okay. Now take note y is 0, but if you will enable this, y receives a. If you will disable, y receives nothing. No. So let's say we have this, no, 1, 1, 0, 0, and when we say enable, yes, it receives. No. If we disable, it doesn't receive. Okay. So it's like a faucet. Any questions so far? Okay. Any questions? So that does everything, no? I'm going to upload that, no, and then we will check. Next meeting we'll introduce a new topic. Okay. Alcantara, Asylum, Walan, you're there.
Present, sir.
Chang, you're there. Chang, Sian, Cordova, not there. Disena, Dishar, you're here.
Present po, sir.
Yes. Digman, are you there? Digman. Eloha, are you there? Ramis is here. Torres is no longer. Gutera, Labuguen, are you there? Langreo, you're here. Lim. Narca, are you there? Narca is not here, no? Navarez, not here. Perez, Perez, you were here. Q, Simon, you're here. Yap, Balmoria. Balmoria. Balmoria, are you there? Mahina ang internet, may luha. N/I lang, no internet. Okay. Balmoria, wala talaga. Okay, Kabuga is present. Yes. Okay. Any questions? So I'll upload this, no? I'll upload this recording. Okay. Next meeting, we'll have a new topic. Thanks, everyone. Okay. Thanks for coming. No? Everyone, that's all we have for today. We'll have a new topic by next meeting. No? Thank you very much. No? Okay, thank you. See you next time. No?